Okay, so we're back for the last short bit of this lecture. And so we left off, we've pretty much talked mostly about what's been happening on the ocean floor, why the abyssal plain isn't this kind of flat, open plain like we thought it was. We talked about the ridges, the mid-oceanic ridges. We've talked about subduction zones. We've talked about seafloor spreading and how the continents spread apart. So up to this point, we've kind of mostly talked kind of more about a little bit about kind of the history of our oceans and how we ended up with the ocean basins that we have today. And so going forward here, we're going to talk a little bit about what our oceans, more about what our oceans look like today and some of those features on not only in the ocean floor, but out in the open ocean. So again, just as a reminder, I'm going to go back through some of these important terms again, because we have to think of our marine environment in terms of, again, 3D, and that makes it more challenging to be able to visualize. So some of these terms that I have here, I've tried to highlight them around with boxes in red. So that way then, these are the terms that are most important for you to know for lecture purposes. So I want you to know, one, what the intertidal zone is. And the intertidal zone is this zone here between the high tide mark and the low tide mark. And so again, these are areas along the shoreline here that are at some point in time throughout the year either covered or submerged by water or uncovered at the very low tide mark. Okay, so again, that intertidal zone is literally between the high and the low tides. So that's the intertidal zone. Then anything that's below that, that's going to remain submerged. Anything that's covered by water is considered to be subtidal. And that can be that it's covered by water in inches, or it could be covered by water in miles. So anything below here is subtidal. Now, typically when we use the term subtidal, just as for reference, we're usually oftentimes talking about things that are on the ocean floor, things that are benthic. So this is another term that you'll need to know. Benthic, and again, we're going to talk about this in lab. Benthic is anything that's on the bottom. Okay, so you can just think benthic. The nice part is you've got your alliteration here, benthic bottom. Okay, so benthic is going to be anything that's on the bottom, and this can be in the intertidal or the subtidal zone. In the vast majority of the organisms that we're going to talk about are actually benthic organisms, bottom dwelling organisms. So then we have the pelagic portion of the ocean. So again, pelagic is going to be the opposite of benthic. So pelagic is going to be offshore in the open water. So anywhere from here to, all the way over here, anything that's living in this open water, we consider it to be pelagic. And when we talk about pelagic, our open water, so again, pelagic, if you want a definition, pelagic would be anything that's offshore in the open water. And we break up our pelagic environment into the neritic and the oceanic pelagic environments. So neritic is going to be anything that lives in these waters which are closer to the shore and over the continental shelf here. And we're going to talk about what the continental shelf is in just a minute. And so that'll make a little more sense. And then oceanic is going to be anything that's living in this water column, which is going to be in this deeper water. And the oceanic realm is going to be anything that's living in the water here, past what's called the shelf break here. And again, we're going to get into that in a minute. And so that will all be oceanic organisms. So those are our pelagic organisms. And so then on top of that, we can kind of differentiate our pelagic organisms by where they are in depth. So we have our epipelagic, our mesopelagic. We won't really talk about the bathypelagic very much just because the majority of the organisms we're going to find here are abyssopelagic. So we're going to focus on epipelagic, mesopelagic, and abyssopelagic. Now, our epipelagic layer, which again will be our epipelagic layer is going to be the layer where we're going to find the most diversity in terms of life. And the reason being is that our epipelagic layer is going to be in the photic zone, and that means that we have the most light that's able to enter this layer called the epipelagic. So this is going to be where we're going to have plankton. We're going to have photosynthetic plankton. This is where we have photosynthetic life. So this is where we're going to, again, see our coral reefs. This is where we're going to see our and again, I know we're talking about pelagic here being open water, but in that water here, even here in the subtidal area, is where we're going to see most of our life. Okay. So that's your epipelagic layer. And then that goes down to about, again, 100 to 200 meters at most. And again, that's part of the photic zone. And then our mesopelagic layer goes down to about 1,000 meters. And again, this is also part of the photic zone. So we still get light mostly, again, at this point in the early mesopelagic layer where we still have light, it's mostly blue light. And we'll talk about that in the next lecture. So that's where we're going to see the majority of her life. And then we have kind of our deep oceanic organisms that would be in the abyssopelagic layer. So those are going to be organisms, again, that are going to be around 4,000 meters down and below. So just to give you, again, some divisions of the ocean in terms of how we classify the ocean. Now, when we talk about the ocean floor itself, we've already talked about the fact that it's dominated by plate tectonics, and this is because of plate tectonics, major features of the seafloor are going to be similar from one area to another across the globe. So we actually divide the ocean floor up into these kind of two major divisions. And that is that we have the continental margins, which are literally just the ocean floor that's submerged as part of the edge of the continent. So these edges of the continents that are submerged underwater. And then we have the deep sea floor, which is going to be our abyssal plains. So when we talk about our continental margins as, again, this first main division, we're going to spend most of our time talking about the continental margins here. Again, that's because that's where we're going to see the most diversity in terms of life. So when we look at our continental margins, and I love this, I wish this diagram was in your book, and I know it's not, so I did include it here for you, so that way then you have this. Sorry, I wanted to actually have my pointer here. So I don't actually want the pen, I just want my laser pointer. But what I want to show you is the great part about this image is that it actually shows you the continental crust and the oceanic crust. And so it kind of puts everything together that we've talked about so far. So, and we'll talk about this at the very end of the lecture. We're going to talk about active and passive margins. But here you can see the continental crust and the oceanic crust meet, but very gently, right? There's no major subduction zone. And that is because this is going to be what's called a passive margin, which means that the continental crust and the oceanic crust are moving in the same direction. They're not pushing against each other and forcing one plate to subduct again underneath another one. Here, they're actually moving in the same direction. And if they're moving in the same direction, this passive margin, we don't see that subduction zone like we would if we have what's called an active margin, where the plates are pushing against each other. But I like this because it shows you your continental crust. It shows you, again, the kind of gradual transition to your oceanic crust. And it will also show you how we actually break up our continental margins. So again, our continental margins are this part of the continental crust that are literally submerged underwater. And we break them up into these three distinct regions. So we have what's called the continental shelf here, which is going to be our shallowest portion. And I'm going to talk about each of these in just a moment here. And then we're going to have our continental slope, which will be this kind of drastic slope down into the deep abyssal plain. And then at the very bottom of that, where the slope kind of gently transitions out to the abyssal plain, we call that the continental rise. So I like this because and then the shelf break here, the shelf break is going to be this point where the continental shelf and the continental slope meet. So then here you can see the continental slope and then the continental rise, and then we enter the abyssal plain. So most of the sediments that have been washed off of land make up the continental margins. And it's considered to be, again, part of the continental margins are considered to be part of each continent's land mass. So here it's just, again, submerged land mass. So we're going to talk about some of all of these features as we go through these three distinct regions here. So again, just another image. This one's actually from your book, so you'll recognize this one, talking about the continental shelf, the shelf break here, then we go into the continental slope, continental rise, and then the abyssal plain. Again, we'll talk about all of these here in just a moment. So let's first talk about continental shelves. And continental shelves actually make up about 7 to 8% of our total oceanic area, which is probably more than you might have anticipated. And they're literally just an underwater extension. You can see here's the continental shelf. I'll follow the continental shelf right along here. All of this is continental shelf, and then down here will be continental slope. So you're going to see that in some areas the continental shelf is wide, quite wide, and then in some areas the continental shelf can be quite narrow, as it is here. So again, it's just an underwater extension of the continent. The continental shelves vary vastly in size. Some of them are, about 400 kilometers if you're talking about off of eastern Canada. You have really large continental shelves there. And then, if you're talking about off the Pacific coast in certain areas, you have, areas where it's just a kilometer. And remember, a kilometer is only about 0.6 miles. So you can have really narrow continental shelves. And of course, this ends at the continental shelf here, ends at the shelf break here. And this is where the slope gets abruptly steeper. And this can occur anywhere from, again, 400 to 1,300 feet deep when we hit that shelf break. So the continental shelf is really important because this is obviously the most biologically richest portion of our ocean. This is the part that's teeming with life. This is where we're going to do our fishing. This is where we're going to find our coral reefs. This is where we're going to find our kelp forests, our seagrass beds. So this is the continental shelf is where we're going to see the majority of our life. It's really biologically rich. And again, as we talked about, it's just part of the continental crust that happens to be underwater. Now, there are different features of this continental shelf that we'll start to get into. So we can see submarine canyons through the continental shelf as well into the continental slope and things like that. But so we'll talk about some of these features like we see off of Monterey Bay here in our continental shelf in just a little bit here. Or actually in this slide. So during past times, especially when the sea level was low, the continental shelves were more exposed. And what happened is rivers and glaciers often flowed through that continental shelf, actually eroding these very deep canyons. And then as, again, the sea levels rose and glacial melt occurred, as the sea levels rose, these then canyons, these deep canyons, then became what we call submarine canyons. And they'll continue, we'll talk about how they're continually eroded as submarine canyons. So now this submarine canyon is actually Monterey Canyon. It's one of the largest submarine canyons, which extends nearly all the way to Monterey Bay. And so this is kind of cool. They actually got this image from this kind of multi-beam sonar image of the continental margin, again, of this area of Monterey Bay. And the reason that this submarine canyon is so famous, again called Monterey Canyon, is because Monterey Bay has the ability then to send these deep oceanic like ROVs and things like that down into this canyon to actually collect some of these deep oceanic organisms. And so they've done quite a bit of research into what types of organisms you're going to find in the deep sea through the submarine canyon. So it's kind of our window into the deep sea. Continental slope is pretty easy. It's just this really abrupt, steep slope that begins at the shelf break here and then descends down toward the deep sea floor. Okay, so it's a really abrupt slope. And the ocean floor drops again drops to about 3 to 5 kilometers, which is 10,000 to 16,500 feet deep. So again, this is a really steep drop down to the deep sea, basically. And so again, this was just, I like this image because it kind of shows you a little bit of everything, but you can see the shelf break here. You can see the continental slope, and then we'll talk about the continental rise here at the bottom here in just a minute. But then it also shows you some of these submarine canyons as well. Now the formation of the continental rise is fairly simple, and that is that you basically over time have had things like earthquakes, and they've triggered, or again, some major disturbance that has triggered or generated something called a turbidity current. And this is basically kind of like an underwater avalanche of sediments. So again, if you could picture, an avalanche occurring, with a steep slope and snow, that's kind of the same thing that's happening here, but with sediments. And as these sediments, again, move down the slope, they generate what's called these turbidity currents. And they'll flow in this kind of circular motion down the slope and then gently fall here at the bottom and kind of rise into the abyssal plain where they come to a rest. Now, the reason that these turbidity currents end up being important is because they can bring nutrients and other materials from terrestrial environments into the deep ocean. And so this is kind of another way in which what we do on land can be connected to the ocean, both good and bad, right? Because we can bring in nutrients and things down to the deep ocean, but we can also bring other materials like pollution and toxic sediments that can actually be pulled down into the deep ocean. And this is how we are actually finding things like microplastics in our deep oceanic communities. So I'll show you some images of that in just a minute here. So again, and we see this in our submarine canyons, the tides will continue to erode our submarine canyons here, and we'll develop these turbidity currents. And just like the turbidity currents here formed, eventually they settle and form the continental rise. Here in these submarine canyons, they actually can form these kind of underwater like alluvial fans that we call a submarine fan. So this would be kind of almost like what you would see, if we have a wash flowing down the side of some of our mountains here. You'll see this alluvial fan where sediment builds up. Here, it's just underwater. And that's because of these, again, turbidity currents. If we can... Let's see if I can get my slide to advance forward. There we go. Okay, So here again, you can see, and this is really, I like this image from your text because it really shows you what some of these turbidity currents look like. Again, it's this underwater avalanche of sediments. And so again, not only do we get these turbidity currents, but also many of these submarine canyons also get some freshwater input from land. So we call this fluvial transport. And because of that, again, we get the good and the bad. So here you can see here's some fluvial transport here where we're getting freshwater input. But along with that, you know, we are bringing nutrients and things to the bottom, but we're also bringing things like domestic industrial waste, microplastics, macroplastics that are being pulled down. And this is how we end up with, and you please click on this link and take the time to do so and check this out because it's pretty interesting. This is how we literally get these kind of underwater landfills in the deep. And this is also one of the ways in which we are finding microplastics in some of our very deep oceanic fish. So again, kind of the good and the bad with that. And so again, after the continental slope and the continental rise here, then with that continental rise ends up in the abyssal plain. So out here we have the abyssal plain at the end of the continental margin there. So again, the abyssal plain is not part of the continental margin. And the abyssal plain is our deep sea floor. It lies at about 3 to 5 kilometers down. Again, 10,000 feet plus down. And it's relatively flat and covered in sediment. And remember that it's relatively flat, but not totally flat, right? Because it is broken up in several areas by things like our mid-oceanic ridges, okay? Or we have our oceanic trenches. So we'll have trenches here where we have subduction zones. You know, we can also have underwater seamounts here or volcanic islands. So again, there are many different things that kind of can break up this abyssal plain. So the abyssal plain we once thought was just completely flat, and now we know that's not the case. There are features that do break up that abyssal plain. And I thought I do have a website down here on extreme science. Please, we don't have the time in this course, especially in the 8-week course, to go through some of the really cool, you know, life that you're going to find in the deep oceanic abyssal plain. But please go to this website and you can find some of these really interesting creatures like the giant isopods. You know, many scientists are not quite sure why, but we end up seeing gigantism in many of our deep oceanic organisms. And so you can click on this link and go to and look at some of these really interesting organisms that we find in our deep oceanic environments. I wish I had time to go into it because they're just really amazing. So please take the time just to kind of go through some of that. And again, this is just another chart kind of showing, again, how we break up the ocean, just another depiction of this. But I won't go over that again. So the last thing that we're going to talk about is these active versus passive margins, which I've kind of already mentioned here. And this is the fact that the nature of our continental margins very much depends upon the plate tectonic processes that are occurring in that region and whether or not it's active or passive. So an active continental margin is a continental margin that is colliding with another plate, meaning the two plates are moving in opposite directions of each other. And as a result, they're pushing up against each other, right? One plate's pushing one direction, the other plate's pushing the other direction, and they're pushing up against each other. And this is a geologically very active area. So again, we have a plate pushing this direction and a plate pushing this direction, okay? So that's an active margin. And again, we end up with narrow shelves here. So we'll have really narrow continental shelves. We'll have really steep slopes and very little to no continental rise in an active margin. So everything's kind of short and steep, okay? okay, with an active continental margin. Now, our passive continental margins are just the opposite. They're typically located at the trailing edge of a continent's plate movement, which means that our plates are really moving in the same direction. So we have, maybe a continental plate and an oceanic plate moving together. So this maybe continental plate is pushing in the same direction that this oceanic plate is pushing, or vice versa. And so we call that a passive continental margin. And as a result, we don't have a lot of geologic activity here. So we typically have really wide continental shelves. We have very gentle slopes and usually these nice, well-developed long continental rises. So let's look at some of the differences here. Okay, so here you can see, again, in the Pacific Ocean here, we really have an active continental margin, especially up against South America here. And so we have, the one plate pushing in this direction and the other plate pushing in this direction here. And it creates this subduction zone, right, where the oceanic plate is being subducted underneath the continental plate. And so it's geologically very active. We have really narrow shelves, continental shelves here for the most part. We have steeper slopes. And again, we have a trench here because there's a subduction zone. So active margin. Now here, on the opposite side of South America here, we have what's called a passive margin. And again, that's because this plate is moving in the same direction, okay? It's kind of trailing along with this plate. And so because of that, and that's partially because here's the Atlantic Ocean here. And if you remember, there's the mid-oceanic ridge out here, right? Which is making new seafloor and pushing that new seafloor in this direction. So here, the oceanic plate and the continental plate are really moving in the same direction. And because of that, we end up with this nice, really wide continental shelf, a much more gentle slope in comparison to, again, the Pacific side here. And then we have a nice continental rise and a much wider continental rise here. And so those are some of the differences, again, between our passive and active margins. And that will, again, make a huge difference on what the continental margins are going to look like in an active versus passive. So that's it for this one. And we will be back for the second oceanic lecture, which is going to go more into kind of the underwater chemistry, which will be important for, again, understanding how our marine organisms survive in this environment. All right.